Okay, well, by now I think you're pretty familiar with the relative response function phi and the cumulative response function RV of z, which is the integral of the relative response function from z to infinity. So we've been talking about these functions graphically and illustrating how you can put them together in order to calculate the apparent conductivity measured using low induction number instrumentation. So things that you might do would be to see if you can integrate this to get this, but we will kind of leave any further exploration of these relationships up to you. And what we want to do now is we want to consider this problem. You know, as you were reading through McNeill, you probably found that there were some exploration depths that were mentioned. For example, with the EM31, you've got a 3.66, 3.67 intercoil spacing, about 12 feet. And for the vertical dipole, McNeill suggests that the depth of exploration is about 1.5 times the intercoil spacing, or 18 feet, or a little over 5 meters. So here we have a problem which is associated with mine spoil, and we're assuming that we have a acid mine drainage contamination zone within the spoil. And in this diagram here, we're just kind of showing a cross-section. We've got uncontaminated spoil with a conductivity of 4 millimoles per meter, a contamination zone with a conductivity of 100 millimoles per meter, so fairly high. It's an acidic zone, high conductivity. We go down to the pit floor with a conductivity of 4 millimoles per meter, and to keep this simple as a three-layer problem, we assume that the pit floor and the bedrock below, that these materials have the same conductivity, so that the pit floor is effectively transparent. And then we ask ourselves, okay, well, in this particular case, the AMD zone is, the top of the AMD zone is a little bit over this 18-foot detection limit or exploration depth. So would you just say, nope, I can't use the EM31. I'm going to have to use the EM34 in order to be sure that I can detect this AMD zone. So that's the kind of problem that we want to look at. And so again, we're going to take a look at this problem in Excel. We're just using the EM31, the 3.67 meter intercoil spacing. We have sigma 1 of 4 millimoles per meter, sigma 2 100, and sigma 3 for the material underlying that contamination zone, again of just 4 millimoles per meter. The contaminated zone is assumed to be 10 feet thick in all cases. So what we'll do is we'll shift over here to Excel. We have this problem set up here. We're just looking at it again. 4 millimoles per meter for this uncontaminated zone, the uncontaminated intervals beneath it, and then 100 millimoles per meter, or millisiemens per meter for the contamination zone. So as defined, it's set up as a three-layer problem. And so we want to see if we take this contamination zone and raise it or lower it, what does that do to our ability to observe the contamination zone. So what we're going to do is we're going to start off at a depth to the top of the contamination zone, which is equal to the intercoil spacing. That gives us a Z of 1, Z1 of 1, Z2 of 1.82. We have this area under the curve here that we've calculated, which would be the difference, R1 minus R2, and this expression over here. So we know that the contribution of the AMD zone to the apparent conductivity will be in proportion to this area. that we have here. And that R1 minus R2 is 0.18. So it is a relatively small number, but it is, 1.5 times the intercoil spacing, Z, Z equal to 1.5 is right in the middle here. So we're, this is the sweet spot. We know that we really should be able to use the EM31 in this case, no problems. And we can see that when we work this all out, that we get an apparent conductivity of 21.7. This is way above, this is 18.5 millisiemens per meter above the background conductivity if it were uncontaminated. That we measure, the apparent conductivity that we'd measure would be just 4 millisiemens per meter. So okay, no question, we're going to be able to see that. Now if we increase this to 2, or let's see, 24, in other words, twice the intercoil spacing here, then we have a much smaller area. The area is only about 0.07. So the contribution is about 0.07 times the conductivity of the AMD zone. Say 0.07 is not much. We're down below that 1.5 Goldilocks zone, and can we see it? Well, we see here that if we go through the computations for depth to top of 24, depth to base of 34, that we get a conductivity of 10.62. This is also significantly above the background conductivity that we'd see in the uncontaminated spoil of 4 millisiemens per meter. So we're going to say, hey, I can still go out there and use the EM31, no problem. So if we just stuck with that limit, just said, well, we can't go past 1.5 and get usable results, we'd be wrong in that case. Well, let's go one step further. Let's go down to the depth to the top is now 3 times the intercoil spacing. The area from R1 to R2 is just about 0.035. So we've got a really small weighting factor in here, 0.035. But remember, the conductivity is 100. The conductivity of the contaminated zone is 100 millisiemens per meter. So when we go through the computations and we calculate the apparent conductivity, we get an apparent conductivity of about 7.4. We're almost double the background conductivity. So our Goldilocks zone is about 1.5. We've said heck with that. We're down here to kind of an average depth of about 35 or 3.5 times the intercoil spacing, and we're still getting good results. So before you chuck the EM31 as a possible reconnaissance tool to see where the contamination may be, if that's the problem that you're looking at, go through this kind of an exercise here and see what you come up with. So what we saw in summary was, using the Excel spreadsheet computations, is that, at 12 feet down to the depth down to the top of the AMD zone, we get 21.7 millisiemens per meter, so we're 17 millisiemens per meter above the background. Very good. At 18 feet, we're just getting outside the Goldilocks zone. Depth to the top is 1.5 meters. Z equal 1.5 times the intercoil spacing. So we're kind of carrying it beyond the zone of potential comfort. You might feel if you like those rules of thumbs, but this is showing you that that's not going to do you very much good, because you would be just fine. You wouldn't miss a contaminated zone at a depth to top of 18 feet, because it would be over 3 times the background. The apparent conductivity would be over 3 times that of the background. and at 24 feet, more than 2 times the background. At 36 feet down to the top, with a z equal 3 to the top, the z equal almost 4 to the base, way outside the Goldilocks zone. We're still almost twice the background conductivity. So again, kind of a bottom line is when you use these rules of thumbs, they're probably good for casual conversation, general ideas about the depth of penetration, but in actual practice, go through the computations. If you have a high conductivity zone that you're trying to find, even though the difference in the cumulative response functions gives you a small weight, if you're 0.035 times 100, you're almost twice the background. So use rules of thumb cautiously. And that's kind of the takeaway on this. As we just said, the conductivity of the AMD zone being 100 here, even though this weighting factor is only 0.035, we get 3.5 millisiemens per meter. Again, almost twice that of the background conductivity in the uncontaminated areas. So next time we're going to take a look at some software that's developed by Interpex Limited. It's called IX1D, and we'll do some modeling. We'll use all 8 measurements, the 8 measurements that you can get from the EM31, the EM34, using the vertical and the horizontal dipole measurements, and we'll take a look at forward and inverse modeling using a full set of data. So talk to you next time.